So we're going to start with question 1, which is a true or false. And the first question is A, Claisen condensations are base catalyzed. Is that true or false? And this is as opposed to base promoted. You can consider the conditions you use for these reactions or whether or not the base is regenerated to figure this out. Give it another 10 or so seconds. Oh, nice. So all of you said true. And this might not be the case on an exam. I don't know how he formats it, but if you can recognize what a Claisen reaction is, you could figure a question like this out based on that. So this is a Claisen reaction. We'll talk about it more later, but it's basically like Aldol reactions with esters. And then here's the condition. It's kind of a bad circle. Here are the conditions that kind of clue you in on whether it's base catalyzed or base promoted. We're using one equivalent of a base, so we're using a full equivalent, and it's the same down here. It's always going to be one equivalent. And if you're using one equivalent of a base, then it's base promoted. If you use the catalytic amount, then it would be base catalyzed. So that's one thing you can look for to determine if it's promoted or catalyzed. And then in the mechanism, we'll see that the base isn't regenerated. So that's another sign that it's promoted. So that's all to say that this is false. Because it uses a full equivalent. Next one is B. Claisen condensations typically utilize weak bases like sodium hydroxide, or alkoxides are other weak bases that might be used here, as opposed to strong bases like sodium hydride and LDA and such. Okay, so 2 of you said true, 1 false. This one is true. They actually don't use sodium hydroxide like ever. That would kind of be a mistake, but do it briefly. Like again, looking at this Claisen reaction, we're using an alkoxide as our base, and we do the same thing here. And these are relatively weak bases when you compare them to like LDA and sodium hydride and amines. So yeah, we use weak bases for Claisen, just like we used weak bases for Aldol. Next one is C. A Dieckmann cyclization has a faster reaction rate than a normal Claisen condensation. And I don't know if he talked about this in more detail during lecture today, but Okuda brought up Dieckmann cyclizations as if he was going to talk about it last week. I'll go ahead and just tell you guys in case you don't remember or he didn't emphasize it. It's just a fancy way of saying you're doing an intramolecular Claisen reaction. So this is basically saying, is an intramolecular Claisen reaction faster than a normal one or an intermolecular one? And that is true. Because remember, this is something that we've seen in the past. Molecular reactions are always faster than inter. And diacmin is just an intramolecular version of that reaction, so it is faster than a normal one. And last one is D. The most stable rings are 5. Should have said like and or 6-membered rings. And this is something you saw in 112A. Like how stable different sized rings are. I'll give it like 10 or so. Okay. 2 of you said false, 1 true. This one is also true. There's not a lot of details I can talk about to explain this. You can review the chapter from the textbook or your notes from 112A. It's really far back, probably like chapter 5 or 4 or something like that. But it has to do with the bond angles and these. And this is relevant because like if you have multiple rings you could form, then maybe the most stable one would be the one you prefer making. So I want to keep this idea in mind for something later today. Is question 1. I'm going to go ahead and erase this and move on to number 2. If you want any clarification, let me know. I'll go back. Okay, so here we have some Aldol reactions. Because we have aldehydes, ketones, and we're using catalytic amounts of weak bases. So it's just a bunch of reactions. A lot of these, at least these first two, are mixed aldol reactions. They involve 2 different species instead of just one aldehyde or one ketone. So you have to be able to figure out which of the 2 is going to be the nucleophile and which will be the electrophile. And usually one of them is preferred over the other. So in this first one with benzaldehyde and this ketone, which one is gonna be the nucleophile? Which one is gonna form an enolate and attack the other one? The ketone, yeah. And why will the aldehyde not be the nucleophile? You're correct that it'll form on the ketone. But what's wrong with the aldehyde? Or what's better about the ketone? That's okay. So you need an alpha, yeah, the alpha carbon. So this is the only alpha spot on the aldehyde, and there's no hydrogens on that carbon I circled. So because it has no alpha hydrogens, it can't form an enolate. So that's one factor you can look for in a mixed aldol reaction. If one thing has an alpha hydrogen and the other one doesn't, then only the one with alpha hydrogens can make an enolate. That's going to be the nucleophile. And then it will attack the carbonyl carbon of the other compound in something like this. This isn't the whole mechanism. So if he asks you to show an aldol mechanism on the final, don't just draw this. It's not the whole thing, but this kind of helps visualize like how the product forms, at least a little. We're making a new bond at the alpha position, showing that in green. And then remember Aldol reactions. Aldol products are beta hydroxy ketones aldehydes. So they have alcohols beta to a ketone or an aldehyde. So there should be one here at the beta position. And then the rest of the structure, which is just a benzene ring here. Like this. And then you should also show the dehydration product when you're doing aldol reactions. So again, forming a new bond at the alpha position. This time we're forming a double bond on the alpha and the beta position. It looks like this. So don't forget, aldol products always look something like this with an alcohol beta to a ketone or an aldehyde. And then the dehydration product has a double bond on the alpha and the beta carbons. All right. Next one, we have a diketone and we have an aldehyde. We have catalytic base, so we're doing another aldol reaction. Which one of these two, the ketone, or I can say blue, or the aldehyde, is going to be the nucleophile? Blue, yeah. And why is it going to be the diketone? It does have, so yeah, that's the detail that's important. Because this time the aldehyde also has an alpha hydrogen. Kind of going against my color code, but yeah, this hydrogen is more acidic than the blue one on the aldehyde. You should know like rough pK values for both of these. For alpha to just one aldehyde, the pK is about 20, somewhere around there. And then if it's alpha to two different carbonyls, like this red one, it's about 10 or 11, somewhere around there. So it's a lower pK, it's more acidic, which means when you add a base, it's going to prefer taking that more acidic proton. So we're going to prefer forming an enolate here. Even though we can form one with the aldehyde, it's not going to want to react with that hydrogen because it's less acidic. So that's another thing that can make mixed aldol reactions work. If one hydrogen is more acidic than the others, then it's going to prefer reacting there. And then the reaction, like before, will be the same. The enolate attacks the carbonyl carbon of the other species, and we get our same general products. Forming a new bond here at the alpha position. There should be an alcohol on the beta position. And then there should be two more carbons because that was propanol. So it should look like this. And then you can also show the dehydration product. New bond at the alpha position. This time it's a double bond between the alpha and the beta carbon. And then two more carbons like this. So just be aware that these are two ways to make mixed aldol reactions work. If there's no alpha hydrogens on one thing, or if there's a more acidic hydrogen on one thing, then these reactions work. And don't forget about the issues I discussed with mixed aldol on the last worksheet, which I think were also discussed a bit in class. Okay. I'm gonna erase the screen in a second to go on to the last two on this page. But if there are any questions about this, feel free to ask. Right here are more aldol reactions because we have aldehydes and ketones and we're adding catalytic weak bases. Those are conditions for aldol. Now, just like usual, since we're adding a base, it's going to want to take a proton and it's going to take alpha protons because those are most acidic in these structures, like this blue one I've drawn. So like this is going to be an enolate will form. And now I can draw another molecule of this. Is this reaction I am drawing going to be the main one we see that's going to lead to major product? Yeah, no, it's not going to. What's going to be preferred over the intramolecular? So this in blue that I've drawn is something that can and probably will happen a little bit, but it's going to be slower than this intramolecular reaction in red. So like it might be good to be aware that like this probably will happen a little bit, but it's not going to be preferred over the red one because that happens faster. So remember, faster than every time. And then sometimes I suggest doing this with aldol reactions, but like especially when you're doing intramolecular reactions, I think it's easy to miscount carbons. So I recommend numbering the atoms or counting like 3 times if you don't want to number them. I'm going to number like from nucleophile, the enolate, to the electrophile, carbonyl carbon. When you do that, you can see it's 1 to 6, so we're going to draw a 6-membered ring. If I didn't do that, I might miscount it as 5 or 7 or something and draw the wrong kind of product. So it's just a good way to make sure you're on the right track. So here's 1, 2, 3, 4, 5, and 6. And then on carbon 6, that's where the electrophilic aldehyde was. So there's going to be an alcohol here. And then on carbon 3, there was a methyl group. So there's still a methyl group there. And then you can also show the dehydration product. Double bond like this, and then a methyl group down here still. So just be aware that if an intramolecular reaction can happen, it's going to lead to the major products probably. So you should keep an eye out for cases where something like this can happen. Like this next one where we have 2 ketones in the same structure and we have a catalytic base for aldol. But this time, since we have ketones, there are multiple enolates we could form. Like we could form this enolate in blue on the end, or we could form an enolate here, closer to like the center of the molecule in red. Which one of these two is going to like form more and lead to the major product? Because one will be preferred over the other. Red is correct. So blue, I will say like normally, the less substituted one would be more favored. So like, I probably have an example of an Aldol reaction with this structure just because I use it a lot. But like if you did an Aldol reaction with this, you would want to form this enolate on the less substituted side because it's faster to form that, so the reaction is faster. It prefers that. So I'm saying like normally that is the case if you were thinking of like a normal reaction. But when it's intramolecular like this, there's another factor that is a little more important. So let's consider like if this enolate, the blue one, was our nucleophile, let's number the atoms from the nucleophile to the electrophile and see like what kind of product we'd end up with. Yeah, and you might see it already. It leads to a 7-membered ring because it's 1 to 7. No, so just have that in mind. Like that was 7 with blue. I'll write that down. And then if you number from the red one, this is 1, 2, 3, 4, and 5. So that's a 5-membered ring. And I had a true false about this earlier. 5 and 6-membered rings are the most stable. If you have a choice between 5 and 6, 6 is more stable. But both of them are pretty happy and they're better than anything else. So that's why the red one will be preferred. Even though like it forms slower and it's normally not preferred, the ring that forms is more important here than like kinetics. So that's going to be what leads to the major product. And 5-membered ring, ketone. It's 1, 2, 3, 4, 5. Number 5 is where the ketone that was the electrophile was, so it should be an alcohol. And then there's also a methyl group on carbon 5. And then you can also show the aldol product, which looks like this. Or this is the dehydration product, not aldol. I'll just look at the time. Okay. So, and if you didn't cover this in detail, like it might not be super likely to pop up, but it is a thing from the book and you can rationalize it with stuff from 112a. So just be aware of the concept of like 5 and 6-membered rings being stable. So you should prefer making those if you can. Okay. So here I have a mechanism question, and we're starting with a bit of review. We're adding water to an acid chloride. So this is a nucleophilic acyl substitution. And how should this first one start? What should the first step of the mechanism be? Yep, water is a nucleophile. It attacks the carbonyl carbon. And then you also have to push the carbonyl bond up towards the oxygen. So that leads to an alkoxide forming. And you still have the chlorine there. Touched water. And what will happen next? Remember, this is a nucleophilic acyl substitution, so we're trying to substitute, yeah. So the chlorine should be kicked out. We'll reform the carbonyl and kick out the chlorine. Like CO. There is still a positive charge on the water because it has an extra proton. And we just kicked out chlorine, so what'll the last step be? Yep, takes the hydrogen. And it leads to a carboxylic acid. And again, like this is review, it's not super new, but it is relevant to the Claisen mechanism we're about to go over. Hopefully the review makes it a bit easier to digest. And just as like a general note, remember this is kind of like a generic template of a base catalyzed nucleophilic substitution. I remember I said there were like base catalyzed and acid catalyzed mechanisms. They're not like official terms, but they were terms I used. And this is base catalyzed because we just start with the nucleophile attacking the carbonyl carbon. Just to kind of categorize it and might help digest the next one. So on that note, I'm gonna erase the screen to make room to go over the next one because I don't want it to be too crowded. So take a screenshot or just watch it in the recording later if you need to. But yeah, so here we're doing a Claisen reaction, and a lot of the time you probably won't be given this 2 that I'm putting here to say like 2 esters are gonna react with each other, but I'm just giving it as like a hint in case you weren't sure, like that's what's happening here. But in general, like if you see an ester and then you have a 2-step process where it's one equivalent of a weak base, and then you add acid in a second step, those are Claisen conditions. Just like weak catalytic base with an aldehyde is aldol conditions. Okay, and we are adding a base in the first step. So what is the base gonna wanna do? Like what's the first step gonna be? Also, like I said before, remember that Claisen is like with esters. So if you think about that, what was the first step of Aldol reactions? Yeah, the base takes the hydrogen on the alpha carbon because that's the most acidic hydrogen here. And that leads to an enolate forming. And then what would the second step of this be if it's similar to an aldol reaction? And this might help a bit. Remember in aldol, we had enolates, and the enolate would attack the carbonyl carbon of a second, yeah, like this. That was correct. And then you push the carbonyl bond up towards the carbonyl oxygen. At this point, though, it will diverge a bit from the aldol mechanism. So we're forming a new bond here, the alpha position. We have an alkoxide. And we have our methoxy group. And those are the 2 carbons. And what will happen here now that we have our alkoxide? Remember, we started with an ester, which falls into the same class of compounds as acid chlorides, like we just looked at. They're carboxylic acid derivatives. So they all do nucleophilic acyl substitutions. That's the general reaction they do. So like, if this is a bigger structure, but what did we do when we had the alkoxide in the last reaction with the acid halide? Did we protonate it? Did we reform carbonyl and do anything else? Like, I know it's not on the screen, but yeah, because this is another leaving group, just like the halogen was a leaving group. So yeah, we're gonna reform the carbonyl and kick out this methoxy, because that's a leaving group. And remember, if we were doing aldol, we would have protonated that alkoxide because we couldn't reform a carbonyl. But here we can because we have a leaving group. So that's the big difference between aldol and Claisen. And then you end up with a ketone. And this structure here is actually the final product, but for the mechanism, it doesn't stop at this stage. Because what we just kicked out was methoxide. And this isn't a great leaving group because it's a pretty strong nucleophile and a pretty strong base, so it's fairly reactive. And there is an alpha hydrogen here, which is alpha to both ketones, or the ketone and the ester. So since it's alpha to 2 things, it has a pretty low pKa. That's a fairly strong acid. We have kind of strong base here, not super strong, relatively. So there's going to be an acid-base reaction here that you can't stop. Even though this is the final product, this always happens. You can't stop it. Well, I guess it wouldn't happen if there wasn't an extra alpha hydrogen there, but most of the time there will be. And then how do we deal with this enolate? There's one more step to the mechanism. Yep, the acid. That's where the second step comes in. It just protonates it, gives it back the hydrogen that it lost. And I'll draw the product here. Actually, I'll just draw it in orange to make it stand out. So this is the product in orange here. And this is the full mechanism. And it'll always look exactly the same, just with different structures. So it would be good to practice drawing by hand a few times to get familiar with it. And I can't guarantee anything like will or will not be on the exam because I don't know what Okuda will put on it, but I will say As far as I can tell, like both before and after I took the class, I think Claisen mechanisms, like he asked to do it on almost every single year he taught the class. And last week when he was talking about this mechanism in class, kind of sounded like he was emphasizing it a lot, like all of the fine details, almost more than he usually does. I could be reading into it, but it just makes me think he's probably going to put it on the final. So I'm not saying it will be because I can't guarantee it, but I think it will be on the final. So this is something that it would be good to be comfortable with. And it is a little tricky because if you don't remember, like, well, if you remember, like, this is the product, so you must be done, that's not the case because this acid-base reaction that I showed is always going to happen. So I think that's part of why he likes putting it. It's really easy to forget that last step there. So yeah, just a little piece of advice. Yeah, it seems kind of redundant, but like when we kicked out the leaving group here in the last step, that's what led it to the OCH free minus. And then this is a relatively strong base. So like you can't stop it from taking that hydrogen because that hydrogen is pretty strong for an acid. It has like a pK of 10. And that's why you need this second step, and it has to be a separate step to add acid just to put the hydrogen back. So yeah, it seems pointless, but yeah. And you might notice like at the end of this, we protonated our base here when we did that acid-base reaction. So in the end, our base was converted to an alcohol. We got methanol here. So the base is gone. It doesn't get regenerated. And that's what I was saying earlier when I talked about like base catalyzed versus promoted. The base is gone. It's not regenerated, so it's base promoted. You can also tell it's promoted because you use one equivalent, but this is why you use one equivalent, because you don't get it back. Okay. And sorry to info dump, just one last thing, so I don't have to say it later when we're talking about Claisen. Actually, I'm gonna erase the screen and then say this. So take a screenshot if you would like. I'm gonna redraw the product just so it's easier to show this. So if we look at the ester here, this is the alpha position, and this is the beta position. So the ketone is beta to the ester in the final product. And just like aldol reactions always, every single time gave you like an alcohol beta to a ketone or an aldehyde, a Claisen reaction is always going to give you a ketone beta to an ester. It's like a characteristic product, just like aldol. So this is just good to be aware of, because if you have that in mind, it's kind of like cheating, like you have a rough idea of what the product should look like. So it makes it easier to figure out what it should be if you know ketone should be beta to the ester. And like we'll have a bit of practice with that on the next question. Okay. No more info dumping on this mechanism. And like if there were any other questions about the mechanism, feel free to ask. I can redraw anything that you have a question about, but otherwise I'll keep going. So The rest of these are also going to be Claisen reactions or similar to Claisen reactions because we have esters and then we add one equivalent of a weak base and an acid in a separate step. It's just a bunch of Claisen reactions. I'm going to approach these the same way I did with the Aldol reactions. So like this is the alpha position on this ester, which means like when we add our base, we're going to be forming an enolate here. I'm kind of skipping some steps and like drawing the mechanism, but this is the enolate you're going to end up with. And then we're not adding any different esters, so it's going to attack another copy of itself, which I am showing in red. So it will do an attack like this. Something like this. And just like with Aldol, I just want to emphasize I'm not showing the full mechanism when I show this. So if you were asked to show a mechanism for Claisen on a test, don't just draw like this enolate doing this attack. That is one step, but it's not the whole mechanism. So that would be an issue. But this helps visualize what's happening. And with a structure like this, I think it's a good idea to number the atoms in the electrophile. You don't necessarily have to, but I think it's a good idea. So I'm numbering it like this. The carbonyl is 1, and then 2, 3, 4, 5, and I'm all numbered in product. So we are forming a new bond at the alpha position in green here. Remember, there should be a ketone on the beta position, so I'm just going to draw that in here. And then you should have the rest of the structure. So this is 1, 2, 3, 4, and 5, and I'll put the numbers there. So this numbering is kind of arbitrary, and you can use letters or whatever else you want to label them. But I just think it's a good idea to avoid like adding the wrong number of carbons when you do this, because it's really easy to miscount when the structures get this big. And, you know, again, if we're looking at ester, this is alpha, ketone is beta to it. So it follows that characteristic structure. Okay. Next one is going to be similar. It's an ester, we're adding one equivalent of base and then an acid. So I'm going to form an enolate here. And then the enolates will attack the carbonyl carbon of the other ester because we're not adding a different one. Again, I'll number these kind of arbitrarily. Draw the product. Okay. Again, forming a new bond at the alpha position. You have a ketone at the beta position, and then this is 2, 3, 4, 5, and 6, and I'll label those. Just checking your work with the numbers helps you make sure it's correct. Okay. So I'm gonna erase this in a second to move on to the next one. And I know it seems like I'm going slow, but the rest of them will probably be faster because it's a lot of repetition of these reactions. So hopefully start getting the flow and it'll be easier. But if I go too fast and you have a question, just stop me, ask, please. I want it to be clear to you all. Okay, so this is actually a little different of a reaction. We have a carboxylic acid and a ketone, and we're heating it, and that's all we're doing. And I just want to point out, like if we're looking at the ketone, this is alpha, and this is beta to it. So they're beta to each other. What's going to happen to this structure? Like what kind of products are we going to get when we heat it? And this is a bit of a weird one, but it is also kind of a review. Yeah, sort of. So I won't show the mechanism because I don't think I have time, but basically what happens is circle it in red, and it is on a past worksheet if you want to review it. But like we're going to lose the carboxylic acid as carbon dioxide. We lose everything I circled in red as carbon dioxide. That's what happens when you heat a structure like this, where you have a carboxylic acid beta to another carbonyl. So in the end, you lose the carboxylic acid and its carbon. This is the product you'd end up with. And then you also make carbon dioxide, which is a gas that goes away, kind of drives the reaction. But this is like the big part that you care about. And I kind of said it, but I'll also write it to emphasize it. This can happen if you have a carboxylic acid beta to any carbonyl. So it could be another carboxylic acid or a ketone or an aldehyde or an ester, just any carbonyl. If it's beta and you heat it, you lose the one carboxylic acid as carbon dioxide. But that's like the caveat. They have to be beta to each other. So if I had like this structure, with the ketone shifted a little bit, and I heated this, nothing would happen because the carboxylic acid isn't beta to the ketone. It's too far away. So they have to be beta. Okay. Next one is another Claisen reaction. And I know I kind of just jumped. If you have a question about the decarboxylation, feel free to ask, but otherwise we'll keep going. So this one's a mixed Claisen reaction because we have two different esters reacting with each other with Claisen conditions. Just like mixed aldol, like when we do these, we want one ester to be more of a nucleophile and one to be more of an electrophile. And the factors that control it are going to be like the same as aldol. So like in this one, I'm a bit low on time, so I'm just going to kind of say it. This is going to be the nucleophile, the one on the right, because the ester over here on the left, this is the alpha position and there's no hydrogens there. So it doesn't have any alpha protons. It can't form an enolate. just like when we had aldols and something didn't have an alpha hydrogen, it could not make an enolate. So that's what's going to happen here. Oh, and this is a little bit of a detail. I don't think it's super important this semester, to be honest, because he hasn't been emphasizing it. But like the base we use when we're working with esters should match the ester. So like this is a methyl ester. There's a methyl group attached to that oxygen. So we use a methyl base, like there's a base attached to that oxygen. This is an ethyl ester, ET is for ethyl. That's an ethyl base. So like the base should match the ester when we're doing Claisen. If it doesn't, there can be a bit of an issue, but yeah, I don't think that's super emphasized, but just like maybe be aware of the general idea that they should match usually. And they didn't here, like the two esters didn't, so I just wanted to correct that. Okay, but for the product, we're forming a new bond here at the alpha position. We have a ketone beta, and then the benzene ring here. And that's the product. And I didn't really talk about it, but we have H2SO4 here instead of acid, like H3O plus for the second step. But this is just another strong acid, like H3O plus. So it's going to perform the same function, and the reaction is going to go the exact same way it did before. Okay. And, you know, again, this is a beta keto ester for the product. All right. I am going to erase this to make room, go down to the next couple. Okay. So here, the second step with H3O plus has a bit extra. There's also water and heat. And that is important, but I'm gonna take this like one step at a time. If you were doing this on a test, you might recognize that like the H3O plus here in the second step and the first step being one equivalent of base with an ester, like those are Claisen conditions. So this looks at least partly like a Claisen reaction. Let's show what we would get if this was a Claisen reaction. So I'm just saying like it's like if you saw that on a test, you could start with that. You could just draw the product from a Claisen reaction. So we form an enolate, and then we have another carbonyl. It's going to be attacked. And in the end, we're forming a new bond at the alpha position. There's a ketone here. And looks something like this. But there are extra components to the reaction this time. We have water and heat with the acid in the second step. So like if you just drew this Claisen product, you'd probably get partial credit because this is a thing that happens. And I'm assuming he'd be nice and give points for that, but it will do a bit extra. Yeah, it will do a hydrolysis reaction. So yeah, when you have water with an acid catalyst and you have an ester, that's going to do hydrolysis. It's going to convert it to a carboxylic acid. So that becomes an ester, water. And then what will be one last thing that can happen to this structure? Yep, we're heating this, and if you look at the ketone, this is alpha attached to the green start point, and then the carboxylic acid is beta. Remember earlier I said if you have a carboxylic acid beta to any carbonyl and you heat it, you can lose it. You lose the carboxylic acid. So that's what's going to happen with the heat. So you heat it, you lose carbon dioxide, and in the end, this is what we end up with. So the green is the new bond we formed to the electrophilic ester that we started with, and then red is like all the other stuff we added. And we lost the carboxylic acid as carbon dioxide. So that's why that's just gone. So yeah, just be aware that like this is something that can happen with Claisen products, and you can do other things with them too, but this is just one thing that I think is more common to toss on a test. Adding the acid, water, and heat instead of just acid can change the product quite a bit, as you can see. Okay. Next one is kind of like a mixed Claisen reaction, because we have an ester, we have one equivalent of weak base, but this time we have a ketone here instead of another ester. So it's not two esters reacting with each other, so it's not exactly Claisen. It's like a mixed Claisen reaction. In terms of like the mechanism, it is gonna look like a Claisen reaction. The only difference is like the enolate, it's gonna form here on the ketone. I'll draw this. It's a little better. But the enolate is from a ketone, it's not from an ester. So that's going to affect the final product a little bit. But in terms of like the nucleophilic attack, it should look something like this. And the ketone forms the enolate because if you look here, that's the alpha position, there's no hydrogens there. So just to emphasize that. Hydrogen, no enolate. Okay. So forming a new bond at the alpha position. And this is one that I think it might help to like do the full mechanism on your own to make sure you understand like why it goes like this. But remember like from the mechanism, the electrophilic ester, like that leads to an alkoxide when you have like this arrow pushing towards the carbonyl oxygen, you form an alkoxide. And then to reform the carbonyl, we kick out this part of the ester. Like that's just describing the mechanism. And like you do that to reform a carbonyl. And then when you do that, you get a ketone. So we're going to get a ketone from the ester there, because that's the electrophile here. And this is the product. So there's two ketones here instead of one ketone and one ester. And that's why I say it's like a mixed Claisen reaction. I don't think you would call this a Claisen reaction because it's not two esters reacting with each other. And the product isn't a Claisen product because there's no ester. But this is something that can happen. You can have stuff besides esters reacting with esters in Claisen-like reactions. And then you can get two ketones beta to each other. Or like if you have an aldehyde reacting with an ester, you'd have an aldehyde and an ester beta to each other. Like it just depends on what your nucleophile is. Like it could be a variety of things. And Okuda might have talked about these sorts of mixed reactions in class a bit today. If he didn't, that might mean you don't have to worry about it actually, but I don't know because I didn't get to see the lecture yet. And I'll let you guys know like after break if you actually have to worry about stuff like this or not, because he'll have talked about it if he wanted you to know it, most likely. Okay. I'm gonna erase this and move on to the last one on this page. And then we'll just have one more question on the last page. So here we have two esters in the same structure, and we're adding one equivalent of a base and an acid. So Claisen again. The base is going to lead to an enolate forming at the alpha position. This could react with an ester in another molecule, but there's an ester right here. So it's going to do an intramolecular reaction like this. And like usual, I recommend numbering your atoms from the nucleophile to the electrophile like this. When you do that, you see a 5-numbered ring. And ketone here, and I'll number that. That's 1, 2, 3, 4, 5. So this is an intramolecular Claisen reaction because you have two esters beta or two esters in the same molecule, and you have Claisen conditions. So that's a Claisen reaction. And remember, not all intramolecular reactions have a special name, but Claisen does when it's intramolecular. And unfortunately, you have to be aware of it. So intramolecular Claisen reaction is called a diagonal. So just be aware of that little detail, that it has a name. Okay. I'm gonna erase this and go on to the last one. So here's a sort of synthesis problem where I'm giving all the intermediates, and yeah, the first step is a mixed Claisen reaction. So we're just filling in the blanks. So I'll just go over it in a bit of detail, so make sure like everybody understands. We're starting with an ester, we end with an ester and ketone, and they're beta to each other. So because the ester and the ketone, like this is the product, and they're beta to each other, this looks like a Claisen product. We could make it from a Glycine reaction. And that is the easiest way to do this. So that's how I'm going to do it. And in terms of like working backwards, like figuring out what to react here on the arrow with this ester, let's look at the ester. This is alpha, and this is beta. So the bonds that we formed to make this product, the new carbon-carbon bond, is this one, highlighted in green, the bond between the alpha and the beta carbon. Just like with aldol, where like I would break the alpha beta bond and like see what we get to work backwards to the starting materials, we can do that here. So you can like kind of put an imaginary line through this bond to break that bond. And then we'll see what two things we combined to make this final product. So on the left, we have this circled in blue, which looks similar to this. This is an ester, that's a ketone, but this is what happens to the ester. It becomes a ketone, so that's accounted for. And then on the right, we have this circled in orange. So that is what we reacted with the ester I circled in blue to make this product. I'm gonna draw the arrow down here just to give a bit more room. So the first step in this is adding 1 equivalent of base along with the other ester, and then in the second step we add acid. So I'll just draw the ester in. Since to draw it there. Okay. So these two esters reacted to make that product. And good job identifying that pretty quickly. Okay, so next we're going from this beta keto ester to a product with just 1 ketone. And we lost 1 carbon. So yeah, you want to add water and acid to convert the ester into a carboxylic acid. And then you also want to heat it to lose the carboxylic acid as carbon dioxide. So you guys got that. Water, acid, heat is what goes here. Because again, like that's going to convert this, put it over here. Water converts it to a carboxylic acid, then heat loses it as carbon dioxide. And last step, we're converting the ketone to an alcohol. So yeah, we're doing a reduction, and that is a reagent we can use. But remember, this is a 2-step process. So the first step involves NaBH4. Yeah, the second step is acid. That's correct. And it's important to remember the second step because if you go over the mechanism of this, which might be good to review since it's been a while, but when you add the NaBH4, it leads to an alkoxide. So without adding acid, you'd be stuck with a negative charge. And you never want to be stuck with a negative charge. And just in case, like another thing you could have done instead of NABH4, it's LiAlH4 acid in a second step. That's another set of reagents you could use, which does the same thing. So that's the end of the worksheet. If you have any questions about number 5 here or anything else today or anything at all, feel free to ask. Otherwise, yep, happy Thanksgiving. I won't be here Thursday, again, letting you know, so don't come to Zoom. But if you have a question over break, feel free to ask by email. Any last minute questions for me before I end the meeting? Raise here, or you can just like type a wait or something. I'll wait like 30 more seconds if you have anything. Okay. See you guys next week.